Good evening, guys. So please type in the chat box. Is the audio and video fine? I guess the chat box is not fine. Just a minute. Yeah. So please type in the chat box. Is the audio and video fine? Okay. Yeah. So let's start today's session. And today is the closing class of applications of thermodynamics actually. And I think this is the last class of this fast track as well, I guess, right? Ramanan sir might have finished the syllabus, or Ramanan sir has class tomorrow as well. Okay, so anyway, for this subject, this is the final class of this applications of thermodynamics, and today is lecture number 11, and we will focus on this compressible flows part 2 actually in this case. Okay, so in last class, actually this is last class, great. Okay, so we'll discuss certain nice important things at the end of the class also, how to do the revision, all the stuff. Okay, so let's see compressible flows part 2. So in last class we have introduced compressible flows. Okay, so we have introduced compressible flows actually. So we have seen basically the flows in which density variations is greater than 5%, or in general Mach number is greater than 0.316 whatever. Okay, so we have calculated this value. So Mach number, emotional moment, see here. So Mach number greater than 0.316. Okay, so this is 5%. Density variations are more than 5%. Then we have seen, depending on the types of depending on the values of this Mach number, we have classified the flows as transonic, subsonic, transonic, and also supersonic flows. Okay, so transonic and also supersonic flows. So basically, typical Mach numbers here is more than 5. Supersonic, and also we have seen hypersonics. Yeah, hypersonic. Okay, so here typically Mach number you have more than 5, and here somewhere in between 1.2 to 5 in general. This means this is around 0.8 less than Mach less than 1.2 of course, and this guy is Mach less than 0.8 of course. Okay, so nearly close to 0.9 and all, we can have these things. Okay, now let's see if these are the types of flows. And in last lecture we have also discussed about the stagnation properties. Stagnation properties, we have seen stagnation temperature by T at any location is 1 plus gamma minus 1 by 2 Mach square. We have shown you this actually. And stagnation pressure by pressure at any point is this expression, power gamma upon gamma minus 1, correct? Because P power 1 minus gamma into T power gamma is constant, because we are dealing with isentropic flows. And density variations, stagnation density by density is 1 plus gamma minus 1 by 2 Mach square whole power 1 by gamma minus 1. So these are the relations that we have seen in the last class. So at sonic conditions, or at Mach number is equal to 1, which is sonic condition, we can see these conditions are given by Ts by T star actually. So this value is gamma plus 1 by 2, that's it. Okay, and P star or P stagnation by P star is equal to gamma plus 1 by 2 whole power 1 by or gamma upon gamma minus 1 actually. And density stagnation by density star, this value is gamma plus 1 by 2 whole power 1 by gamma minus 1. Now depending upon the type of gas, you put the value of gammas. So depending on the type of gas, you put the values of gamma. For monatomic 5 by 3, for diatomic 7 by 5, and for triatomic 4 by 3, you can calculate these values. I think for atmospheric air we have taken gamma is equal to 1.4 and we have calculated this constant values. I think this came out 0.8. This is 1.2. 1.2. 1.4 plus 1 by 2. Okay, so 2.4 by 2. This value is 2.1 by 2 something we got. Okay, and this is 0.833. We got certain numerical values, right? Is this clear to all of you? Yeah, these are the conditions, right? Stagnation by temperature. So T star, if you put Mach is equal to 1, so this is gamma plus 1 by 2. So 1 by 1.2 is what we have reciprocated. T star by Ts, all these values we have seen. P star by PS, O star by OS. Okay, so we have seen all these conditions. And then after, we have also seen one important relation that acoustic velocity in any medium is dou P by dou, normally we write it as partial derivatives at isentropic conditions, and for ideal gas we have seen A is equal to square root of gamma RT actually here, okay, and we have seen P by O, this value dou P by dou, because this for ideal gas dou P by dou at isentropic conditions is equal to gamma RT is what we have seen actually in the last class, okay. So in today's session, if you see, we will basically focus on area versus velocity relations. Means let's say if there is a compressible flow and if we have a nozzle, okay, so in this nozzle how the flow actually happens, okay, so how the Mach number gets transferred all over the flow, and how pressure variation, temperature variations, how to calculate at any location, okay. So that's what we will see. Then isentropic flow through nozzles, again we'll see a couple of nozzles, converging and also converging-diverging type, and we will also find some details of normal shock in today's class, okay. So normally questions never touched, questions are not touched beyond this point. So these are the points which I am planning to cover in this case, and in the last we will wind up the complete subject, okay. So this is the plan for today. So we will start with area and velocity relations. So is this clear to all of you? And also we'll solve numericals of compressible flow today in the class, okay. I have set some 4 to 5 good numericals which we can solve based on the knowledge we have, okay. So this is how the class is going to be for the next 2 hours roughly, okay. Do you all have your notebooks which we have written till this particular point in the last class? Then we will see from this point, okay. Yeah, Ankit, Loha, Subhash, Vitam, Beam, all of you, Vivek, yeah, okay. So let's see, so let us see this case of area versus velocity relations, okay, in case of compressible flows. In compressible flows, okay. So this is in your compressible flows. Now let's see, you have certain cross section, maybe it can be diverging or converging, depends, okay. You have some cross section. So at this point, let's say this cross section is A, okay. So it is A1 maybe here, and this is A2 over here, okay. So this is isentropic flow, clearly there is nothing, no heat interactions, nothing we are touching up. So this is actually a isentropic flow actually. Good evening, Rexo. Okay, so see here, let's say the fluid enters like this and it flows over this cross section, then it flows over this passage. So you take a small section to analyze what happens to this fluid velocity, okay. So let's say you take a small section of length dx along the length of the nozzle, so let's say at this point. So over this small length, the variation in the velocity or the variation in the flow area dA is area elemental change in flow cross section, elemental change in flow cross section, okay. So elemental change in your flow cross section, and let's say dV is the small elemental change in velocity, elemental change in velocity. Means let's say for example here if the velocity is v, then here it is maybe v plus dv, okay. So something like this. And clearly since this flow is compressible, because of this flow effect, density also changes. So do is variation in density. Let's say this is variation in density, okay. So this is variation in density. Clear? Because normally it's a compressible flow. So because of this small area change, it is rho into mass flow, it is constant actually, rho into A into V. So because of this change in area, velocity will change, and also since the fluid is compressible now, density can, means the flow is compressible, so density can also change. So let's say dA, dV, dO are the changes in area of cross section, velocity and density in the flow. Now let's say if the amount of fluid which is flowing is m dot actually here, okay. So m dot is the mass flow through this section or channel. So let m dot is mass flow rate to the passes, and this m dot is actually constant because at any point if you take at any element, for example if you take this small element do not have enough volume to hold some amount of mass, okay. So definitely whatever is coming in, some other the same quantity should actually leave. Means if you take this small amount of volume actually inside this, then definitely this volume has to be under steady state operation. Clear? So what is the mass flow rate to this? M dot is equal to rho at this point if the area is A, and this velocity is v, for example. Okay, so exactly at that location, if the velocity is v, area is a, and O is there, then definitely for small movement, for small change in x length of the nozzle, then a changes, v changes, and also O changes. So if you differentiate this, derivative of m dot is equal to, you know, product of three functions. So first two into derivative of third plus first and last into derivative of second plus second and third into derivative of the first actually here. Okay, so this is the differentiation. Okay, so differentiation of product of three functions. If you divide with m dot, this is rho AV, and here also we have rho AV actually here. Then you can see these two gets cancelled, and this dm dot is actually 0 because m dot has to be constant at any given section. Okay, so this 0 implies d rho by rho plus dA by A plus dV by V is actually 0 at this case, correct? So I want to talk some important things, so I'm doing a bit of derivation here, just, you know, 5 to 10 minutes it takes, but it's an important derivation, that's why. Okay, so let's say this is equation number 1. So mass has to get conserved definitely. So d rho by rho plus dA by A plus dV by V is equal to 0 is the continuity equation. And normally in case of incompressible flows, what we do, we make the first term 0 and we have this equation, which you might have seen. If you integrate, you will get AV is equal to constant. Okay, again this. Okay, fine. Now let's see energy balance. So if you apply steady flow energy equation, because this block has to be under steady state, this part of the system has to be under steady state. So del Q minus del W is equal to change in kinetic energy plus change in potential energy plus change in enthalpy. Okay, and since this is adiabatic nozzle, okay, so it's a, adiabatic passes, definitely del Q is actually 0, and that don't produce any work, so this is 0. And let's say if you are neglecting potential heads. Okay, so I have already told you in fluid mechanics, this steady flow energy equation is same as the Bernoulli's equation, okay, in case of adiabatic things. But anyway, here if you see derivative of change in elemental kinetic energy, so this is nothing but derivative of half V square, correct? So this gives you V into dV. So the first term gives you V dV plus this second term dH. dH, if you write it as dH, for example, V dV plus dH is equal to 0. And since the flow is isentropic, we can use the TDS equation. TDS is equal to dH minus V dP actually, which we are using in all the, you know, this Rankine cycle, all the cases. So if this is 0, your dH can be replaced with V dP, and this is dP divided by density actually. Okay, so dP divided with density. Now in this equation you can see this gives you V dV plus your dH. dH is nothing but dP by O. dP by O is equal to 0. So this is your second equation. Okay, so this quantity is your equation number 2. Because see, my intention is to see, depending on this area of cross section, if you have certain inlet conditions, what could be the things after that. Okay, so if possible, tell about your journey. Okay, I'll do that. Okay, if time is left, then definitely I'll do that. Okay, but you know my side, generally time is not left. Okay, so what we are doing, yeah, so this is basically continuity and this is the energy analysis. Now if you try to couple these two, let's see what happens. See here carefully, we know this dA by A is equal to minus d rho by rho minus dV by V actually here. Okay, so minus dV by V is what you have. Now let's say, because of this equation, if I take this dV by V common, dA by A is equal to minus dV by V times of, okay, so minus dV by V times of 1 plus d rho by rho is what you have here, correct? So 1 plus d rho by rho actually here, that's what you have. Now let us see how you can convert this d rho by rho actually. Oh sorry, I think we also have something like into V by dO. Okay, that's what, because sorry, V by dV actually. Okay, so this is V by dV, of course, correct? Because see, if I am taking dV by V out, then definitely I should divide this with dV by V, which gives me a multiplication of V by dV. Okay, so are you all clear till this point? So please tell me. What I have done is basically I have done the continuity equation and using energy equation, then I'm trying to couple these two, that's it. Okay, so this is what I'm getting. Is this clear to all of you? Yes or no? So please type in the chat box. Yes or no? Come on, type in the chat box. Is it clear to you till this point? Just continuity equation and steady flow energy equation, and I'm trying to couple these two equations. That's it. Nothing I have done big. Okay. Now actually, to further simplify this equation, we need something of this dO by dV. Okay, because V and density of conditions at a particular location. But what is the ratio of this dO by dV? That's the main thing which is important. Okay, but we ideally don't have the values of dO by dV. So let us take the help of this equation. V dV is equal to dP by rho actually here. Okay, but we want d rho by rho actually. Okay, so let's say if you multiply dO and d rho here, this actually gives you see dO by rho. Okay, I think we can adjust a bit here. See, we have acoustic velocity, because I want to convert this into Mach number, because this is dimensionless, and of course this dimensionless combination I want to convert to Mach number actually. You can see we have acoustic velocity is equal to Mach number equal to acoustic divided by velocity. So if you square these things, we have Mach square is equal to this a square dP by dO into V square. Okay, so this V square, if you multiply it here, into 1 by V square. Okay, now let us see, dP by dO is what we have, V square into Mach square. So yes, if you convert this, then this gives you something like dA by A is equal to minus dV by V times of 1, because of this term d rho by rho into V dV. Guys, just a bit of maths, just do it. dA is by A is equal to minus dO by O minus dV by V. So if you take minus dV by V constant, we have 1 plus dO by O into V by V dV, correct? That's what you'll get, dO by O into V by dV. Now let us try to manipulate this quantity. V by dV is what you want. Okay, so we have this equation, V by dV. So what we can do here, let's see, or let's try to do one more thing. This acoustic is dP by dO, correct? So acoustic velocity is dP by dO. What we have here, from this we got V dV is equal to dP by rho. So V dV is equal to minus dP by rho actually. Okay, so into rho by dO, rho by d rho actually. Okay, so if you have this, then this density and density gets cancelled. This combination is acoustic square. So this tells me rho by dO into V dV is equal to minus acoustic square. So that tells me d rho by rho is equal to minus V dV by acoustic square, correct? So this is the equation. Okay, just a bit of mathematical adjustment. See here, this is your acoustic velocity square. Okay, so you have V dV is equal to minus dP by O. From this equation you can see V dV is equal to minus dP by O. So V dV is equal to minus dP by O. So if you multiply this O by dO and O by dO on both sides, this density gets cancelled, and this dP by dO gives you acoustic velocity square. Okay, because this A square is equal to dP by dO. So rho by d into density into V dV is equal to minus A square. So if you flip this equation, or if you take this dO by O to the other side, dO by O is equal to minus V dV divided by A square. Okay, so in this equation, if this dO by O, let us substitute this, minus V dV by A square into V divided with dV. So this is what you have. Now dV and dV gets cancelled here, and you have dA by A is equal to minus dV by V into 1 minus V into V is V square divided by A square, which is Mach square. Yes, okay, that's it. Okay, so this is the relation. A bit of mathematical adjustment, that's it. Okay, see, okay, this is in how Mach number conversion. Basically I want this value of dO by O, but I don't have it directly. So by using a bit of simple manipulations, I was able to get the value of this term in terms of velocities and acoustic velocities. Is this clear to all of you? So please type in the chat box. Is it clear to all of you till this point? Yes, because I don't have the value of this directly, I want this in terms of velocity and acoustic velocities. I have done a bit of adjustment in this term. Is this clear to all of you? Anyone want me to repeat, or is it fine? So please type in the chat box. see what we have done is basically you have this equation. So in this equation you have shifted this minus dp by O to the right hand side and multiplied O by dO. That's it. Okay, because I want to convert this in terms of dimensionless combination, and we have done. Okay, in terms of Mach number. Now if you see one important thing, we got this equation dA by A is equal to minus dV by V into 1 minus Mach square actually here. Okay, so this equation is a bit of important because this equation helps us in understanding designing these channels. Okay, so let's see, this is the final equation. Now try to understand few things here. For subsonic flows, where Mach number is actually less than 1 actually. Okay, so for subsonic flows when Mach number is less than 1. So try to understand, if you have 1 minus Mach square, this will be definitely greater than 0. Yes or no? If Mach number is less than 1, then this quantity will be definitely greater than 0, because square of something which is less than 1 will be less than 1. So this is positive. So this implies, since dA by A is equal to minus dV by V into 1 minus MA square. Now try to understand, this term is actually positive. For dV to be greater than 0, this implies, see, if I want to increase my velocity, means in this passage, let's say if this is V and this is V plus dV, for example, at this point, if this dV has to be positive, means if velocity has to increase, then see in this equation, for this quantity to be greater than 0, minus of something greater than 0. Now what should be this quantity? What should be dA? Greater than or less than? Can anyone tell me? From this simple math, you can see this quantity is greater than 0, and if you want a positive increment in velocity, if dV has to be positive, area and velocity are always positive. So what should be dA? Should it be positive or negative? What should be dA actually? It should be positive or negative here in this case? Just type in the chat box. This term has to be positive or negative here. dA. All of you. Negative, right? So dA has to be negative in this case. Yes? So dA has to be negative. So this dA has to be negative. So that means for velocity to increase, area has to decrease. Definitely area has to decrease. That means your nozzle, if along the length, if your area of cross section is decreasing, that means the type of nozzle for accelerating the flow in case of subsonics is converging nozzle. Okay, so you can see, therefore to accelerate the flow in supersonic or in subsonic regime, we need a converging nozzle. We need a converging nozzle actually here. Okay, so we need a converging nozzle. So that's why normally in all the fluid mechanics problems, normally in incompressible flows cases and all, since the Mach number is much less than 1 actually, so you can see even if you apply this analysis for accelerating the flows, we see the nozzles are converging in, and in all converging water pipes we see the velocity is increasing. Normally if you take a pipe for example, if you press it and reduce the cross section, then the velocity will definitely increase because of this. Okay, now let us see, if you have a converging nozzle, how parameters get changed. Okay, so if you have a converging nozzle, okay, and this is the case of subsonic flows, subsonics. Okay, so this is subsonic, and let's say here the properties are something like V1, P1, T1, ρ1, okay, and maybe say density and Mach number 1, let's say this is Mach 1, and here if you see V2, P2, T2, ρ2 and Mach number 2 in general. Okay, so this is Mach number 2. Guys, don't feel the Mach number is same here and here, because I'll tell you why. Mach number is fluid velocity by acoustic velocity. since temperature is changing between these two locations, so definitely acoustic velocity is not same at these 2 points, and also fluid velocity is not same at these 2 points. So clearly the Mach number need not be same at these 2 points. Understood? So Mach number may keep increasing, or it can happen generally. Okay, we'll see what happens here. Now let's see. If you see one important point, this is subsonic and this is converging nozzle. Converging nozzle. You can see this is a converging nozzle actually. So if this is your converging nozzle, then let's see, V1 will be definitely less than V2. Yes or no? Because dA is negative, so definitely dV has to be positive because of this. So as you go in this direction, velocity increases, correct? So velocity increases. Velocity increases. Okay, so velocity increases. Now, can anyone tell me what happens to temperature? Come on. Can anyone tell me what happens to temperature? So tell me what happens to your temperature? What do you feel happens for your temperature in this case of flow? Will it increase or will it decrease? Or will it remain same maybe? Increases or decreases? Think a while and just answer. Come on, every one of you, give it a thought. Okay, same. Decreases or increases? Fine. Let's see. You know, if you apply steady flow energy equation for this system, definitely you'll end up with dH plus change in kinetic energy is equal to 0. Okay, so this is what you'll get. Yes, so dH plus d into Ke is equal to 0, and this gives you Cp dt. Of course, you're talking about ideal gases, plus V dV is equal to 0. So V dV, or maybe you can say dt is equal to minus V by Cp dV. Of course, you can convert in terms of gamma relations and everything. So if you do this, then clearly you can see this dV is coming out to be positive. Yes. So if dV is coming out to be positive because of this minus sign, what should happen to dt? Dt should be negative, correct? If dt is negative, so dt is negative, then what's happening to your temperature? Come on, answer this. If dt is negative, then what happens to your temperature at this? Come on. Okay, so there's an ideal gas which is flowing inside. Okay, we are doing the analysis only for ideal gas as of now. So what happens to your temperature? It should come down, correct? So temperature should actually decrease. Okay, so T decreases, so T1 is actually greater than T2. Temperature decreases. Temperature decreases actually. Now what happens to pressure? That's the important thing. What happens to your pressure? So let's see in this equation. So basically in this maybe in this equation, you can see dP is equal to minus rho V times dV, or maybe you can see even in this equation here, dA, this implies dA by A is equal to minus dV. So what is dV actually? If you see, V dV is equal to minus dP by O, so dV is equal to minus 1 by OV dP. So this dV minus dV can be written as, see, minus of this minus dV, which is here, can be written as minus d, or dV is equal to minus 1 minus dP by rho V. So minus dP by rho V actually. Okay, so minus dP by rho V into this V actually. Okay, so you have this V, of course, into 1 minus Mach square. 1 minus Mach square. So if you simplify this relation, we have V into V, of course. So dA by A is equal to dP by rho V square times 1 minus Mach square is what you have here. Okay, and when you are in the subsonic regime, then definitely this Mach number is less than 1. So Mach number is actually less than 1. If Mach number is less than 1, this quantity will be positive. If this quantity is positive, anyway these two guys are positive, then definitely if area is decreasing in case of this case, in case of converging nozzles, you can see area is actually decreasing. This is A1 and this is A2, and converging nozzle A2 is less than A1. Okay, so if area is decreasing, then this dP should also decrease. Okay, so pressure in this case will actually decrease. So P1 is actually greater than P2, and pressure decreases. Okay, so is this clear to all of you? Yes or no? Come on, type in the chat box. Can you understand that this quantity P1 greater than P2, how this is happening? Yes or no? Please type in the chat box. Okay, so what do you think about density? Rho1 and Rho2. What do you feel will happen to density actually? What do you feel will happen to density in this case? Density will increase or decrease? Think. You know something. Look here. This is the most important point. Okay, so what happens to density? That's your main understanding. Tell me. Tell me what happens here. In this case, density decreases. Sure. How? See guys, it's simple logical. Okay, nothing very big, calculative and all. It's purely logical. Okay, you see what we are doing. If this is positive, this is negative, then my positive into negative is negative. That's how we are deciding the things. Okay, so come on, you can tell this. What happens to your density? Think. These are the interview questions. Okay, they'll ask you what happens to your density. Everyone knows this condition. They all know velocity will increase. But what happens to pressure? What happens to temperature? What happens to density? These things are important here in this case. Okay, so see carefully. Density also decreases. We'll see how density decreases. Let's work it out. Okay, before we write, because let's work out some things. See, we have d rho by rho is equal to minus dA by A minus dV by V from continuity equation. Okay, so minus dV by V from continuity equation. Okay, now this term can be replaced in terms of density. See here, dA by A is equal to minus dV by V times 1 minus max square is what you have. So if you replace here, minus dA by A minus dV by V can be written as minus dA by A into 1 by 1 minus max square. Okay, so this is what you get. Yes, correct? Can I write this? All of you, please type in the chat box. This dV by V, whatever is there, since we have calculated this relation, this dV by V can be replaced with minus dA by A into 1 by 1 minus max square. Can I do this? Yes or no? So please type in the chat box. Can I do this? Yes. Now let's see. D rho by rho is equal to, see, this is minus dA by A. This minus into minus gives plus here. If you take dA by A common, we will have minus 1 minus of minus plus 1 by 1 minus max square actually here. So this value gives you, okay, so d rho by rho is equal to dA by A times, if you take LCM, max square minus 1 plus 1 by 1 minus max square here, and these two terms cancel each other. Then this term gives d rho by rho is equal to dA by A times of max square divided by 1 minus Mach number square. So this is one relation again which you can identify, and in this equation you can see if d rho by this term is decreasing for subsonic flows for Mach number less than 1, you all know this 1 minus max square is positive. Okay, so this denominator is positive and this is a square quantity. Rho, density, this density, area, all are positive. If dA is decreasing, means if case of converging nozzle, for converging nozzle, if you have a converging nozzle, if dA is negative, then definitely these two should have same signs, so dO should also be negative. Okay, so this gives you density decreases actually. See, simple bit of 2-3 steps, but if you do analysis, you will see rho actually decreases, so density decreases. See, you cannot analyze this using ideal gas equation, okay, because P by RT or P by OT at first state and P2 by O2 T2, if you see here temperature is decreasing and pressure is also decreasing. Okay, so that's why you cannot justify basically here. Okay, so that's why your temperature actually decreases, velocity increases, and densities decreases actually. And Mach numbers, can anyone tell me what happens to Mach numbers? Mach 1 and Mach 2 normally in this case. Come on, decide and tell me what happens to your Mach number. Mach number 1 and Mach number 2 means at the inlet, this is the Mach number 1. Of course, I have written already MA1 and MA2. So can someone talk about what happens to this? Sir, name Lalijiye, sir, name is, yes. So I didn't get this. So please tell me, what do you think happens here? Will it increase or decrease? Velocity of the flow is increasing. Okay, you clearly know velocity increases for subsonic case, in this case of a converging nozzle. Then what about the other parameters? I mean, what about this Mach number? What do you feel will happen for this Mach number? Come on, tell me. What do you feel will happen for this Mach number? Mach number will increase or decrease or remain same? Decreases, paka. This actually increases. Okay, so you will see Mach number actually increases. Mach number increases. I'll tell you the reason. See how you can easily understand how Mach number increases. Yeah, Mach number clearly increases. Okay, so how this Mach number increase? Look, you all know Mach number is equal to velocity by acoustic velocity, and which is velocity by square root of gamma RT actually. Okay, now as you go along the flow direction, velocity is increasing clearly and temperature is actually decreasing. Okay, you can see clearly velocity increases, temperature decreases, then this quantity, total quantity, increases along the flow direction because numerator increases and denominator decreases. So as you go, it increases, and finally there comes a limit where it touches Mach is equal to 1. Okay, if you keep the nozzle for good enough length, then what happens? The flow finally accelerates and it touches the sonic condition where Mach is equal to 1 actually. Clear to all of you? Yes or no? Is this clear to all of you? Did you understand this or not? Yes? Okay, so these things you need not mug up actually. You see enough logic is there behind each and every equation. Okay, so if I want to summarize, basically, you know, for isentropic flows in a passage, for isentropic flows in a passage, you can understand dA by A is equal to minus dV by V times 1 minus Mach square. Okay, so this is what we have here. Then we have also, so this is that equation. From here we have also seen dA by A is equal to, dA by A is also equal to dP by rho V square times of 1 minus Mach square again. Okay, so 1 minus Mach square, that's what you have got here, 1 minus Mach square. Now coming to density variations, we have just worked out dO by O is equal to, or dA by A, you can say dA by A is equal to, dA by A is equal to, dA by A is equal to dO by O into 1 minus Mach square by Mach square. 1 minus Mach square by Mach square actually. Okay, so these are the properties which helps you in identifying whether pressure increases, velocity increases, temperature increases, all these things actually. Okay, is okay, admit card aaya hai kya? Haan, yes, it got a list. Okay, fine. Now let's see. So therefore you can see in case of converging nozzles for subsonic flows, and for supersonic flows. For supersonic, if you do the same analysis with Mach number more than 1, signs will be opposite, that's it. Okay, because 1 minus Mach square will be negative this time. Okay, so for subsonic, in case of converging nozzle, okay, so this table what I'm giving you, you need not mug up, but because of these equations you can simply analyze this. Okay, so for subsonic flows and in case of converging nozzle, you can see velocity increases, temperature decreases, pressure decreases, density decreases, and Mach number increases. Okay, if this is the case, then definitely for supersonic what happens? Mach number is more than 1. So if you put in this Mach number more than 1, these quantities will be negative this time, and definitely signs will be opposite. So here in this case, if you draw a table like this, then okay, now clearly you can see in this case your velocity will actually decrease, temperature increases, pressure increases, density increases, and Mach number decreases actually. Okay, Mach number decreases because it's a just opposite case of this actually here. Okay, and if you look at diverging nozzles, then this set which is in supersonic for converging will repeat here, and this set which is for subsonic will get repeated here. Yes or no? Simple understanding, right? Yes or no? So please type in the chat box. Let's say if I am applying for diverging, if this dA is positive, now means if the area of cross section is increasing, okay, so the channel is diverging channel, then definitely whatever the conditions we got in this case, because mathematically just minus into minus will again give you plus, so whatever is in this condition that comes out here. Correct? Yes or no? So please type in the chat box. Come on, Suki, Loha, 𝐂𝐤𝐧𝐤𝐬, Yogesh, Vivek, Rohit, all of you. So yes? Yes or no? Can you understand this? Because see, for example, if I have diverging nozzle, in this case, Mach number is more than 1. If Mach is more than 1, this quantity is negative. Okay, so if this quantity is negative, negative of negative is positive. So these two should have same signs. Okay, so if these two should have same signs actually, then if area of cross section is decreasing, then definitely velocity also has to decrease. Okay, velocity decrease in case of subsonic diverging will also come here. Similarly, all the other properties. Okay, so velocity decrease, temperature increase, pressure increase, density increase, and Mach number decrease. Okay, so clearly here also, because if velocity is increasing and temperature is velocity is decreasing and temperature is increasing, Mach will come down, and this set will repeat here, which is velocity increase, temperature decrease, pressure decrease, density decrease, and finally Mach increases. That's it. Okay, so based on these conditions, lot of questions comes in GATE examination and also in other exams actually. Okay, they'll give you what is Mach number, what is the type of the nozzle, then they'll ask you these options: velocity increases, density decreases, pressure decreases, all these properties they'll ask you, and also Mach number, they'll ask about the Mach number, what happens to your Mach number. Even there's a question in GATE 2023, I would like to solve it live for you. So let's see, GATE 2024. Let's open the official website. I hope all of you can see the question paper. Download. Okay, then 2023 mechanical paper, let's open. So if you open mechanical paper, then let's see the nozzle diagram. It's there somewhere. Yeah, here it's going up. So you can see this is the question actually here. Okay, so you see, consider an isentropic flow. I hope all of you can study this actually. Okay, you see, consider an isentropic flow of air where specific heat. Can you all see this question? Yes, I hope all of you can see this. Okay, if you cannot see, I'll just increase the brightness for some time. Okay, so fine. Okay, now I hope you all can see this question to some extent. Consider an isentropic flow of air, gamma is 1.4, through a duct as shown in the figure. The variations in the flow across the cross section are negligible. Okay, the variations in the flow are negligible. The flow conditions at location 1 are given as below. Okay, so P1 is 100 kilopascals, density is 1.2, U1 means the velocity of the flow at this section is 400 meters per second. The duct cross sectional area at location 2 is given by A2 is equal to 2A1, means basically it's diverging. Okay, where A1 denotes the duct cross sectional area at location 1. Which one of the following statements about the velocities U2 and P2 at location 2 are true actually? Okay, fine. So let's see this. They're asking you what happens to your velocities U2 and P2. Let us take this question. Let's see. If you work out, see what happens. There is a diverging passage. Clearly this is a diverging passage. Okay, so this is a diverging passage. Now at this point we have got P1 is equal to, so P1 is equal to 100 kilopascals. Rho 1 is density of the air, which is 1.2 kg per meter cube, 1.2 kg per meter cube, and velocity U1 they have denoted with U. Fine, U1 is 400 meters per second actually here. Okay, so this is 400 meters per second. Then what happens at this point? Okay, so to understand what happens at this point, we should know what is the Mach number at this inlet conditions. Yes or no? So what is the Mach number at this point? Mach number is equal to u1 by acoustic velocity 1. So u1 divided by square root of gamma r t1, and gamma rt can be written as p by o. You can do that, p1 by rho 1 into gamma actually. Okay, so because you know acoustic velocity for ideal gas is root of gamma p by o. If you calculate this value, 400 divided by 400 meters per second divided with square root of gamma. So they told gamma is 1.4. They have given ratio of specific heats is 1.4 in the question they mentioned. Okay, ratio of specific heats is 1.4. 1.4 into P1. So what is P1 at this point? 100 kilopascals. So 100 into 10 cube. Why I am putting 10 cube? Because this is in meters per second. So even I have to write every quantity in normal SI units, not in terms of kilos. What is density? 1.2 kg per meter cube. So this is 1.2. So if you simplify, this Mach number at the inlet of this nozzle is actually how much? 400 divided by, if you do calculation, let's see, 400 into, sorry, first let us simplify the denominator, 1.4 into 100 into 10 cube, 10 power 5, so into 10 power 5, so this value divided with 1.2, okay, so 1.2, so square root of this value, now reciprocate this and multiply 400, so you see Mach number at the inlet is 1.171, 1.171 actually here. Okay, so Mach number is 1.171. That means this flow is actually supersonic at the inlet. Supersonic at the inlet actually. Okay, so if this flow is supersonic at, yeah, 1.171 we are getting right. So if this is 1.171, then the flow at the inlet is supersonic. Mach is more than 1 and the passage is actually diverging. So let's go to this condition. Supersonic and also diverging means this set of points are important for us. Yes or no? Out of these four sets, diverging cross section with supersonic flow is this combination. So in that particular combination, they're asking about the what are the important things they're asking? U2 and P2 compared to U1 V1. So velocity increases, so definitely U2 is greater than U1, and pressure decreases, so P2 is less than P1 actually here. Okay, so that's it. Clear? Did you understand how we can work out the questions? See, because of this analysis, whatever I taught you now, we identified these are the conditions that are going to turn out depending on the type of the flow and also the type of the nozzle. Then this is the diverging nozzle with supersonic flow at the inlet. Then we have this. How many lectures will take to complete just compressible flows? Because I'm learning from your lecture and this topic always very good, but your teaching is on fine. Okay, so this topic, if I want to teach completely, it takes, you know, it's a separate subject actually. Fine. So, but as of now, today is the last lecture. Whatever is needed for GATE, I'm telling you. Okay, so don't worry. Fine. So whatever is needed, I'm telling it for you. Clear? So U2 greater than U1 and P2 less than P1 actually. Okay, so if you see U2 greater than U1, so U2 greater than U1 and P2 less than P1. P2 less than P1. So option C should be the correct answer of this question. U2 greater than U1 and P2 less than P1. Option C is the correct answer for this 20th question. Let's see. Definitely you will have this 20th question. So C should be the correct answer. Let's check it out. Oh, answer key is not given. Answer key is not there after this. Fine. Okay, but later you can check. Anyway, if you have the key, you can easily check that. Yes. So you can understand clearly. This is what you will get. Okay, if you have official key, you can check. Definitely C is the correct answer because we have solved it live in last year. We know this. Okay, so U2 is actually more than U1 and P2 is less than P1. So these kind of properties, you know, variations are always important. Clear to all? Fine. Okay. Now let's see. We had these conditions actually in last class. We were talking about these conditions. Okay, so these conditions, stagnation, PSUs, all these are very much useful for us actually. Okay, now, so are you all clear with this point? Yes? Are you all clear till this points? Yes or no? This is bit of compressible flow at this level. Basically, is understanding a bit of mathematical equations. Okay, for GATE as of now. That's it. If you go into much details, you have gas dynamics and advanced gas dynamics courses, which could take you in depth of all the types of flows and all, but as of now I hope it's clear. Okay, and these three equations are really important. They, you know, help you in deciding the things. very much. Okay, now let's see isentropic flow through nozzles. Of course, the same thing which we were talking about, but here one thing, it's not passes. We have came to a clarification that they are nozzles actually. Okay, now let's see. First case, we will talk about the converging nozzles. Converging nozzles actually. Converging nozzles. So if we have converging nozzles, then what happens actually? So lecture notes upload कर दीजिए. हाँ, definitely ना. Lecture notes will definitely get uploaded. अच्छा, Telegram पर ठीक है. I'll try to do that. Okay. So converging nozzles. Yeah. Let's see. If we have a converging nozzle, for example, say something like this. If you have a converging nozzle, and let's say the inlet to this nozzle is maybe from some reservoir. Okay. So there is some reservoir here, some reservoir of, you know, gas actually. I'm slightly trying to reduce this because I want to draw some more things. Just a minute. Okay, yeah, down I can put some things. Now see here. So let's say this is a nozzle. This is converging nozzle. Okay, of course this is converging nozzle. And here the conditions are stagnation conditions. Okay, T0. Normally stagnation properties are denoted with a symbol naught in the bottom. Like this is stagnation temperature, stagnation density, stagnation P0. Means basically this is at a rest condition. Okay, and normally if you see, whenever you have a big reservoir, the inlet velocity at this entry of the nozzle will be very much small actually. Okay, so because of this small velocity inlet, we can almost state this is very much compatible to you know, static conditions and stagnation properties. Okay. So according to BSc exam, max age is 26 and currently I'm 25, but by April 1st I would be 26. Am I eligible to apply? Yeah, I think so, because generally they will put the age limit as per the last date of the application. But anyway, in detailed advertisement you can just go through it. Okay, I think the detailed notification is out. We will open at the end of the class and we'll have some idea. So see here, these are stagnation properties. Stagnation properties. Now let's say if I start doing my experimentation. Okay, so what's my experimentation is basically, this is your exit pressure, means the pressure at the exit of the nozzle. Pressure is my exit of the nozzle, PE. And normally let's say at this discharge, let's say if this is discharging into some tank actually, so at this point the pressure is PB, which we call back pressure. Back pressure actually. Okay, so there is back pressure. We'll see there is some small difference between this PE and PB, which we will analyze now. But let's say this is the exit plane, pressure at the exit plane, and this is slightly just before the exit plane. So at the point of discharge, what is the pressure of the gas that we are maintaining? Okay, so what is the pressure at this point? Now let's see, I want to ask you a few things. This is the length of the nozzle along this location. Okay, so let's say if this is section, or this is the beginning of the x coordinate, and you have certain length of nozzle, some sufficient length. Okay, now let's say if I plot the quantity, PB by P0 actually here at this point. Okay, so PB by P0 means PB is this and P0 is this actually here. Okay, and you have PB here at this case. Okay, PB at this case, clear? PB by P0 is here, and PB normally you are plotting at you know, the other case. If you see, if this value is 1, okay, means if this value is 1, or let's say this is P0 initially. Okay, you have P0 along the variation you are studying, pressure variation along the nozzle. So here it have P0 of course, and there it is PB. Okay, so PB. Now try to understand, if I maintain PB such that this PB is same as this P0. Okay, so just try to understand, if I keep this back pressure, means the pressure at this point is just equal to P0, because here this P0 is the highest pressure that it can have because of the static condition. Complete energy is in the form of this temperature and also pressure. Here this PB is the back pressure. If I maintain these two equal, okay, so let's say this back pressure is very much as strong as this P0, then will there be any flow that's happening in this nozzle? So for PB is equal to P0, for PB is equal to P0, what do you think happen? Will there be any flow which is happening in this nozzle? If these two pressures are same, then will there be any flow that effectively happens from left to right? Come on, type it in the chat box. if you are applying a very P0 same as PB, then will there be any flow that takes place in this case? Because the pressure is balanced at both the cases, okay? So there is no pressure difference for the gas to flow from one point to another point. Correct? So the pressure along the nozzle length will be same all over, okay? So this will be same as PB because it's uniform at every location, and whenever this is uniform at every location, then definitely there is no mass flow which happens. For PB is equal to P0, there is no pressure variation. There is no pressure variation. There is no pressure variation that happens that occurs along the nozzle, along the length of the nozzle, along the length of the nozzle, along the length of the nozzle, and m dot mass flow rate at this point is equal to 0 straight away. Okay, so mass flow rate at this point is equal to 0 clearly. Now let's see. Now let's say this PB is initially here. P0 is same because the tank condition is nothing we are disturbing. But let's say now a separate experiment I'm doing. This PB initially which is equal to P0, now I have reduced it to some less quantity. Okay, so let's say this PB I am reducing it to a bit low values. So let's say this is my new PB. This is my new PB. Then will mass change? I mean, will flow occurs and will there be m dot then? Yes or no? Let's say if I am decreasing this PB and there is pressure difference between these 2 points, then will the gas start flowing from this point to this point? Yes or no? Yes or no? Yes, definitely it starts flowing, correct? Definitely it starts flowing actually. And if you see the pressure curve, the pressure trace occurs something like this. Okay, so this actually decreases. So you can see maybe somewhere here. So this is your PB. So this is your PB. Now, because because of this pressure drop, flow occurs and there is a variation of the pressure along the length of the nozzle. Now I want to ask one thing. So at this point there is some mass flow rate which is flowing at this point, m dot. Okay. Now let's understand few things. If you want to calculate this m dot, what is this m dot? At any section in the nozzle. So let's say at any section in the nozzle, for example, say at any section in this nozzle, maybe you can take at any location. If the mass flow rate is m dot, because it cannot escape out, so it is isentropic. Okay, so we are talking only isentropic nozzles and all isentropic flow. We are not allowing any heat interaction, and this is reversible. Okay, so if this is m dot, how you can calculate m dot actually? M dot at any point is equal to rho into a into velocity. Correct? Can I say this? Mass flow rate at any section is given by product of density into area of cross section into velocities actually. Okay. Now let's see if this is rho AV. I can write this m dot is equal to, because density is not directly known, from this we'll calculate generally we can calculate pressure and temperature directly. Density we have to calculate again, but pressure and temperature can be measured directly. So let us convert in terms of pressure and temperature. Rho can be written as P by RT into area. What is V? V can be written as acoustic velocity times Mach number, and acoustic velocity is square root of gamma RT into Mach number. Let's say if there is only ideal gas. Okay, so only ideal gas, so acoustic velocity we are writing directly as A into Mach number, and this A is square root of gamma RT. So this V can be written as square root of gamma RT into Mach number, correct, at that particular location. Okay, so let's say at this particular point you have Mach number, so we have Mach number. Now tell me, if this RT simplifies this, we have m dot is equal to P by square root of RT into area into square root of gamma times Mach number. So this is the mass flow rate. Okay, but anyway you can understand one thing. This gas during its motion, pressure may change, temperature may change, but one thing that remains constant is these two quantities will never change. Yes or no? At a given condition, so P0 and T0 will never change, correct? Because they are the stagnation values, they are the energy values, means these two quantities corresponds to the energy of the gas actually. Okay, so since energy cannot be destroyed or created, this P0 and T0 will actually depend at a given state. Let's see if I am maintaining this tank at P0, T0, at any point in this flow, definitely if I calculate the stagnation properties, since see here the fluid is static condition, let's say if the fluid is moving like this, at any point in the flow, if I stop this flow and if I make these particles, if I bring these particles to rest again, if I measure again P and T, they will be same as P naught and T naught. Yes or no? Yes. At any point in this flow, if I stop the flow, means if I make the flow again adiabatically to rest, and if I measure pressure and temperature, the values will be same as P naught and T naught. Correct? Yes or no? Type in the chat box. Fine. So please type in the chat box actually. Can you all understand this? See, initially the gas started from these stagnation properties and it started to flow. At any point, if I stop this flow, means at any point, let's say if the particles are moving in this direction. So at this point, if I again bring the flow to adiabatically at rest, then definitely my pressure and temperature will be P naught and T naught actually. Okay. Now let's see. If I convert this, we know P naught by P is equal to 1 plus gamma minus 1 by 2 Mach number square whole power gamma upon gamma minus 1, and T naught by T is equal to 1 plus gamma minus 1 by 2 Mach square actually here. Mach square actually here. Okay. So these two quantities can give me something as T is equal to, or T is equal to T naught into 1 plus gamma minus 1 by 2 Mach square whole power minus 1, and P is equal to P naught times of 1 plus gamma minus 1 by 2 Mach square whole power gamma upon 1 minus gamma, because this gamma minus 1, when you bring this quantity here, okay, so P naught into, if you bring this quantity here, this gamma minus 1 can be replaced with 1 minus gamma. If you substitute these two in place of this P and T, see what you will have. M dot will be equal to, I am just writing this thing, P can be replaced with P naught into 1 plus gamma minus 1 by 2 Mach square whole power gamma upon 1 minus gamma into flow area into square root of gamma into Mach number, this quantity divided with, now coming to this square root of temperature, so R into this T can be replaced with T naught times 1 plus gamma minus 1 by 2 Mach square whole power minus 1. So this is the function that finally you have for the calculation of mass flow rate at any point in this nozzle. Correct? Yes or no? Means depending on P naught and PB, depending on the pressure variations, at any point, if you want to calculate the mass flow rate, of course, mass flow rate is same across any length, but at any situation, for given values of P naught and T naught and flow area, if you calculate this quantity, we can see P naught into 1 plus gamma minus 1 by 2 Mach square. You got some relation in terms of Mach numbers, stagnation properties, and fluid properties, right? Because this is area anyhow. P naught is there, T naught is there, Mach number is there, gamma is also there. So these are the variables actually here. Yes. So as you said earlier, we'll cover maths extra topics for XC when we detect. I think around after mechanical exam. Okay, after mechanical and before XC there is certain time. So during that time we'll take. Okay. Fine. So this is the expression. Now in this expression, you can understand one thing. Depending, you can see this Mach number, of course, P naught and T naught are there, and area is also determined. Means let's say for example at this point, at any point, let's say at this point if I am doing this analysis, at this point if I am doing this analysis actually, okay, so if I am doing this analysis here, A at this point, then you can see this A is fixed at any given location for a given nozzle, but depending on this flow parameters PB or P naught, O naught, T naught, one thing that changes is this M dot is fixed, but Mach number along this flow can actually change. Yes or no? Half होगा ना sir? कहाँ? OT. Yeah, correct. By 2 is there. Yes. Because this square root is there. So because of this square root of RT, there is a 1 by 2 here. Correct. Yeah. So 1 by 2 is there. Now let's see one thing. Along this flow direction, one thing that changes is this Mach number, because at any location area is given by some function, or this A is determined. So let's say if you have the design of the nozzle perfectly, this Mach number actually increases along the case. Okay. So if this Mach number, sorry, hello. Yeah. So see here, if this Mach number increases, if you, for example, do this analysis, D of M dot by D Mach number, you will understand this value. If you take 0, then this implies for maximum value of, for max value of m dot, your Mach number will be 1 actually. Okay, if you differentiate this expression with respect to Mach number, I'm leaving it for you, please do this, okay, at some time of your comfort. And doing it is not, you know, pretty simple as well. You have to, you know, do it a bit lengthily. So but one thing that you can understand from the results is, if you differentiate this, because this m dot increases depending on the conditions here. So at this exit conditions, if you change the conditions in such a way that this fluid starts here, and if the flow accelerates, the Mach number at this location, if at the exit of the nozzle, if it turns out to be 1, okay, so if you can decide PB in such a way, look, one thing that you know, it's subsonic flow because its velocity is starting with very low velocities, okay, so Mach number is very small here, and the Mach number keeps increasing along this. Now we are deciding, for having the maximum mass flow rate in the nozzle, what should be the maximum limit at the exit of the nozzle actually here, okay, so that tells you Mach number is actually 1. Clear? This purely comes out from the maths of this. If you differentiate this with respect to Mach number and equate it to 0, you will have Mach number is equal to 1. Okay, because see, all over this part the flow is subsonic. So if this is subsonic, maximum Mach number up to which you can touch is 1. Okay, because using a converging nozzle you cannot go to supersonic limits. Okay, so maximum you can go is touch only up to Mach number is equal to 1, and that's what it gives you. At Mach number is equal to 1, this m dot is actually maximum. So at exit, for Mach number is equal to 1, m dot is equal to m dot maximum actually, and the area at this point, is normally denoted with A star at that case. Okay, so in this expression, if you put A is equal to A star and Mach number is equal to 1, m dot max is equal to, if you put Mach number is equal to 1 here, we'll get P naught times of, if you put Mach number is equal to 1, this is gamma plus 1 by 2 whole power gamma upon 1 minus gamma into A star into square root of gamma, because this is the minimum possible cross section area in a nozzle. So this root gamma into Mach number is 1 again here. So by R times T naught into gamma plus 1 by 2, of course, whole power minus half. So this is the maximum mass flow rate expression that you will get in case of this converging nozzle, of course. Okay, so this is the converging nozzle. The meaning of this statement means, you know, this function has a maximum at a particular Mach number in a converging nozzle. Look, this complete analysis we are doing only for converging nozzles. Okay, so in this case of converging nozzle, at Mach number is equal to 1 means at this exit, because in a converging nozzle this is the area of the minimum cross section at the exit. So at that point the Mach number should turn out to be 1 actually here. Okay, and we know the properties corresponding to Mach number is equal to 1 are called sonic or critical properties. So if you see, if you further increase, if you further keep decreasing P, okay, so if you keep further decreasing P, and if there comes a limit where your PB is actually equal to P star, okay, so PB is equal to P star, which is the static, which is the, you know, sonic property or basically the critical properties. At this point, the pressure variation along this curve, whatever is there, that curve is the curve corresponding to the maximum flow rate in this condition. Is this clear to all of you? So please type in the chat box. Is this clear to each and every one of you? Yes or no? One thing that you understood is, as PB keeps coming down, you have mass flow rate begins at this point and there is some small variations of pressure, okay, but there comes a particular limit for the maximum mass flow rate in this condition, and that limit happens at the sonic properties. And how do you know it's sonic? Because of this differentiation, this derivative gives you Mach number is equal to 1 as the stationary point. Okay, so if Mach number is equal to 1, then, you know, definitely in this condition, if you further decrease this PB, normally when these two are equal there is no flow. If you start decreasing this, then flow starts happening in this case, okay, but there is a theoretical limit. PB is equal to P star is the location of, PB is equal to P star is the situation of the maximum mass flow rate. If you further decrease this PB is equal to P star, flow never changes, okay, the flow will actually stays at that point, okay, means the flow remains at Mach number is equal to 1. And even further decrease in PB, let's say if I want to further decrease in PB, then how you will see the curve is, see, the curve actually follows this path, and then there is a sudden drop at this point. There is a sudden drop at this point, and it comes to PB at this point. Okay, means for PB is equal to P star, if you lower this PB below P star, the situation will be same, means the maximum mass flow rate whatever is attained, that still be there, and there is a sudden drop at the exit of the nozzle. Means the mass flow rate doesn't get affected in the nozzle, and this pressure which is equal to P star correspondingly doesn't get affected. That means the throat or the minimum cross section, normally throat is called the minimum cross section in a nozzle. We have also seen in venturimeters and also minimum cross sectional area, minimum cross sectional area in a flow. Okay, so in a flow, of course. So this is in a flow. So you can see, even if you decrease PB below this value, then definitely we have the same pressure variation in the nozzles. Okay, so my batch is Parakam 2025 English. I studying engineering maths from your lecture at Khazana section. Will the lecture enough for 𝐂𝐸? No, actually. Okay, it's not, because in 𝐂𝐸 there is some 20% of the extra syllabus which I haven't covered there, because that batch is a common for mechanical ECE table. When I have taken that batch, it's like a common engineering mathematics section, so I don't have the time for 𝐂𝐸 then. Okay, but anyway, don't worry of the ECE topics. Once your mechanical exam is done, I'll definitely take certain sessions on 𝐂𝐸 maths. Okay, so don't worry. So did you all understand these graphs? First of all, everyone, can you all understand these graphs? How this pressure, even if you reduce this PB, but this P exit will stay at P star for any pressure below this P star. Understood? So in all these cases, your PB is initially equal to P naught, then it starts decreasing and it touches a limit P star. Beyond that, even if you decrease PB, the exit pressure will be still remaining equal to P star actually. Means if you see this PB or P exit, this P exit will be equal to PB as long as your PB is greater than P star or equal to maybe, and this will be equal to P star for any PB which is less than P star actually. Now did you understand the difference between these two? Because initially when I'm telling these two are two different pressures, there could be some confusion, but actually these two are not same. Okay, they two appear to be same only until this condition where PB is more than the sonic property or sonic pressure at that situation. Clear to all of you? Yes or no? Is this clear to all of you? Did you all understand how the pressure variation happens and how mass flow rate in the nozzle is affected as per this and this maximum flow rate condition? Okay, so this is the situation where you have the maximum mass flow rate, and that's called the choked condition. Okay, the condition of m dot max is called choked condition. Choking means complete block. Okay, so it's like full everywhere in the nozzle there is mass and the nozzle is completely choked. Okay, so choked condition is what you can say. So this is the choked condition actually. Okay, because if m dot is maximum, that means at every point the nozzle is fully packed with mass and it's moving. Okay, and the gas is actually moving. So we see there is no provision in this nozzle which is empty, so it's completely full with mass, so we call that as choked condition. That's it. Okay, so is this clear to all of you? Yes or no? So please type in the chat box. So basically you can maximum you can touch is Mach number is equal to 1 in case of a sonic nozzle. That's it. You cannot increase the speed beyond. Okay, so this is the story of converging nozzles. This is a bit of math which we need to explain the effect of this curves actually. Okay, now let's see, I want to show two important curves. If you see the mass flow rate normally, because I think this could be asked in some cases, if this is mass flow rate actually, and this is the curve of PB by P naught. Okay, PB by P naught. Now clearly you can say, let's say if this value is 1, let's say this value is 1, then for PB is equal to P naught, there won't be any flow, and even if PB is more than P naught, there won't be any flow. Okay, so the line looks something like this along this. Okay, so there is no flow because it's 0 mass flow rate. But as this value comes below 0, okay, so let's say if this is 0 for example, then for any value between 0 and 1, see if I write 0 less than PB by P naught less than 1 actually. That means for any value of this in this regime, PB is actually less than P naught. So that means you always have a flow in that. Okay, so PB is actually less than P naught, means definitely there is a flow in the converging nozzle which is taking place. So what happens here is the flow, as you decrease this PB, this ratio keeps decreasing and you will start to have a flow actually here. Okay, and there comes a situation the flow actually increases with decrease in this PB naught, and there comes a situation where it reaches maximum where this value is P star by P naught actually here. Okay, so P star by P naught, like for air we have calculated this as 0.58 something, no, 0.58 or point, we have calculated in last class, right? P star by P naught we have calculated for atmospheric air. You remember, as far as I remember, it's I think 0.586 or something of that range. Okay, so when you come to that particular value, this mass flow rate attains maximum and it sustains like this. So this mass flow rate, it maintains this maximum value. So this is how the mass variation with respect to the PV and Pmax. Okay, and this is the complete maths which supports this result. Okay, and here you get this m dot maximum, and this happens at this back pressure is equal to P star actually. Clear? And now you can see, so the mass flow actually increases here. Let me draw this curve slightly slow, because if you go into bit of more details of slope and all, this graph looks something like, in the initial part it mass happens very fast. Okay, so mass increase happens very fast like this. Okay, so this is the variation of mass flow rate with respect to this concept of back pressure. Okay, and you can see this is at a given T naught and P naught, for example. Okay, at given P naught comma T naught actually. Okay, so this is at a given P naught T naught. Now let's say if I either increase P naught or decrease T naught. Okay, so if you see, this is the expression which you have, m dot maximum. So if you either increase P naught or decrease T naught, okay, then definitely this mass flow rate will increase. Understood? See, T naught and P naught are here. If I decrease this stagnation temperature or if I increase this stagnation pressure, then definitely my mass flow rate will actually comes up. So if this is the curve at a given condition, now another curve which if I draw something like this, you can see. So this will be the curve something like this. If P naught is increased, or T naught is decreased, actually here. Okay, if P naught is increased or T naught is decreased, definitely at the same value of PV by P naught, definitely your mass flow rate increases. Means if I construct a line like this, then definitely if you see, if this is at a given P naught T naught, if I do any one of these things or maybe both, then definitely at the same pressure my mass flow rate will increase definitely. Okay, so that's what the idea. And clearly for decreased P naught T naught, for decreasing P naught or increasing T naught, the curve comes something like this. You'll see this is something like this. Okay, okay, so this is for the situation of, okay, let me use the same color. So this is for the situation of if P naught is decreased, or T naught is increased. Actually. Okay, so if you do any one of these two things or maybe both, then definitely with respect to the given condition the mass flow rates will actually decrease. Okay, and this understanding can be done from these equations and also this idea. So is this clear to all of you? Did you all understand this concept of converging nozzles? How back pressure affects the flow inside the nozzle? Okay, and the maximum you can get is at the throat, which is this A star. Normally the sonic properties at Mach number is equal to 1. Okay, so at Mach number is equal to 1, the sonic conditions are denoted with the superscript star actually. Okay, so this is what you have, and these values normally we have calculated for air. How much is this for air? I think for air, what is this value at which you can get this? We have P star by P naught is equal to 1 plus gamma by 2 whole power gamma upon 1 minus gamma, I guess. Okay, so at 1.4, so if you calculate this value at gamma is equal to 1.4, so this turns out to be something like 1.2 power 1.2 power, this is 1.4 by minus 1.4, so minus 1.4 by 0.4. okay, so divided by 0.4, so I think we got this value 0.528. yeah, this value is 0.528. 0.528 is what we got. Yes, so at this value of 0.528, this will attain a maximum mass flow rate, and then after, even if you decrease this, the mass flow rate remains constant. Okay, because clearly you cannot do something beyond that, beyond this point. Okay, so beyond this point you cannot change anything, so definitely it locks at that point, m dot max. Okay, now let's talk something about, if you look at the same situation of this diagram. See, here I have done bit of maths and all to explain you how this happens, but in case of converging diverging, I'll directly give you the results. Okay, so in case of converging and diverging nozzles, converging diverging nozzle, converging diverging nozzle. Why there is a need for developing converging diverging nozzle? Because this converging nozzle offers a limit. Okay, so this converging nozzle, you can see this converging nozzle offers a limit actually. Beyond Mach number is equal to 1, beyond Mach number is equal to 1, you cannot increase the speed in the case of a converging nozzle. Okay, but actually if you see in case of rockets and all, this is one very good interesting question which asks, which people ask in some interviews. Normally if you see a rocket, I'm drawing a rough sketch. Okay, fine, you have the side thrusters also maybe. This is the approximate shape of a rocket you might have seen. Yes, yes or no? These are the side thrusters, these are the main thrusters, and you have the body. Okay, this is the shape of the rocket. You all know basically this rocket, within the rocket, it operates on Newton's third law of motion. Newton's third law of motion actually. Okay, so this is Newton's third law of motion. Now let's see, if this is Newton's third law of motion, then definitely if this is the exit gas velocity, exhaust gas velocity, this exhaust gas velocity and of course the mass flow rate, okay, combustion mass flow rate, this decides what is the velocity of this rocket. Yes or no? This V rocket is actually, if you take this V rocket and this is the exit gas velocity, clearly these two are proportional to each other. Yes or no? If higher is the exit gas velocity, then definitely faster will be the rocket motion. Okay, now if you want to, and obviously you need this V rocket has to be as high as possible, as high as possible. Once it crosses the atmospheric belt at least, then after its velocity has to be as high as possible to defy the gravitational belt. Okay, then let's see if this VE is there, okay, and this is V, definitely these two are proportional to each other. Yes or no? Higher is this exit velocity, faster will be the rocket motion. Now if you want to keep increasing the velocity of the rocket, definitely this VE has to be as high as possible, correct? So this VE has to be as high as possible, as high as possible, correct? If this has to be as high as possible, then normally the question that people ask you in interviews is, they'll construct story, okay, they'll tell you till this point, they'll make you accept that these two are proportional to each other. Definitely VE is increasing, VE is increased, then definitely for having highest possible value of V rocket, this VE also has to be as high as possible. Then they'll ask you if you want to accelerate something, because if you want this exit velocity to be fast, okay, or if you want this VE to be very high, then this nozzle is supposed to be converging, because this is the idea that we'll generally have. Okay, converging nozzles will accelerate the flow. Okay, but you can see they'll ask you this question, if you want to accelerate this flow as much as possible, and if you want to throw it out at highest possible velocity, why you are having a diverging nozzle, why you are not having a converging nozzle? This is the question what they ask you many times. Okay, because all our mind, or basically because of lot of incompressible fluid flows, we assume that only these converging passages can actually increase the velocity of the flows. Okay, but the reason is whatever you are seeing outside will have some extension inside something like this. And this nozzles, whatever you have, maybe somewhere combustion here is happening and the exhaust gases are flowing in this direction. Practically what happens is, once it reaches this limit of Mach is equal to 1 at this thought, then for further increase in the Mach number, for further increase in the velocity, what you will do is, you will make this a diverging section, so that at this location, in this locality, study of this thought is very important actually, but right now I'm just telling, if you neglect this small mechanics here, thought is the location where the flow transforms from subsonic to supersonic. Once it enters the supersonic regime, if you want to still further accelerate the flow, then definitely your nozzle has to be diverging. That's why you'll see, if you actually see a rocket nozzle, I'll show you, it's a converging diverging nozzles. Rocket nozzle, I'll just show you this diagram. I think whether I can show you, yeah, some CFD diagrams, and also you can see this is basically the converging part which you cannot see inside, and this will be the outer part. Maybe some realistic images or something could be there, I would show you. Yeah, you can see here the same diagrams, okay, the space exploration, stack exchange, fine, okay. So yeah, 3D printed, you can see this part is actually visible to you, but before that there is a converging section which you have seen something like this, okay, which you have seen something like this, okay. So this is how you have the nozzle, understood? So once flow enters this and it enters till this throat, it accelerates. Beyond that, for further acceleration, this comes out, okay, fine. Did you understand this? That's why we need this CD. Did you all understand what is the necessity of having a converging diverging nozzle? Yes or no? Clear? Yeah, of course, generally we deal within the subsonic regimes, okay, in our day-to-day life, like fluid flows and all. Yes, is this clear to all of you? What is the importance of this converging diverging nozzles? Okay, fine. So at the throat, we have the Mach number is equal to 1 in general. Now let's understand some important things. If you have this nozzle, for example, a converging and diverging nozzle, okay, so if you have a converging diverging nozzle like this, let's see. And this is the throat at this point, okay. So you got a throat like this, fine. So this is your throat, and this is inlet, and this is your outlet. And let's say again, here the pressure is P0, T0 and all. There is a reservoir at conditions P0, T0, ρ0. So here you have PB, P0 actually, and here you have PB, for example, okay. So PB like this. So whenever, clearly if you see, if these two are same actually, okay, so if these two are same, fine. So if these two are same actually, if these two are same, then definitely there is no flow, clear. So P0 is equal to PB, then definitely no flow, as in the previous case. But something that happens here, if the exit pressure PB, I mean this is PE of course, and here you have the PB, okay. So PB, can I erase this, okay, or shall I keep it? Okay, I'm keeping it as of now. So if you see, if this section is back pressure, and here the conditions at this point is P critical, which is nothing but P star of course, okay. So P critical, which is equal to P star. Then for flows which are less than 0, less than PC, less than P star, you will observe there is no flow here of course in this case. But if you slightly reduce PB than this P0, for this case of P0 greater than PB greater than PC, or PB greater than PC, just a minute guys, P naught greater than PB greater than PC. If you have this condition where PC is this condition, yeah, it's okay, Nitin, just follow up the things. So in this case, you will see the pressure variation something like, it starts at this point, it goes till here, it again raises here, like this, okay. So this is how you will get the variations, okay. The variations in this case is something like this in case of converging diverging nozzles. So here, because clearly because of the velocity increasing, then the pressure actually decreases, which we have studied in the subsonic part, and after that then this pressure will actually increase because it's supersonic and diverging, okay. So the pressure actually increases because it should meet this condition, PB is greater than PC, okay. And finally, if you further keep the things, P naught is greater than PB, of course, and this is equal to PC, then there is a sonic flow that happens like this here, okay. So there is a flow which happens like this. If you further decrease this PB, if P naught is greater than PB and P naught is PB is less than PC, so this is the case, okay. So this is opposite to this, okay. So initially you are maintaining this, but let's say if you are maintaining this case, then the flow comes out like this from this nozzle at the supersonic limit, at the sonic limit, like you have seen, and after coming to this point at some location, practically what happens is, see, the flow of this, because of this back pressure, the fluid velocities are controlled, okay. And when PB is actually less than PC, here the velocity will try to increase, but at this locations, if PC is more than this PB, it will try to further push the flow, okay. And there comes a sudden jump in the properties from this location, okay. So there comes a definite location, there comes a situation where there is sudden jump in the properties, and this will be again PB, of course, okay. So this will be PB, and here this is PC. Of course, this point will be slightly less than this because we have told this is the case. So if this is here, maybe somewhere here. So this is your PB actually. So practically what happens is, at this location there is a sudden jump in the properties. A sudden jump in the properties. A sudden jump in properties is what you get. A sudden jump in properties, and this sudden jump is nothing but it's a shock, okay. So basically the word shock is like in a daily usage. Let's say for example you got some 100 crores of lottery, then what happens? You all feel very happy, correct? You will feel shock, and because it's a good shock actually, okay. So because of that shock, your life and your situations will completely change, okay. So similarly here, what happens here is, because of this shock which gets here, there is a sudden jump in these properties because the fluid continuously try to accelerate here, but here it should have certain conditions, okay. So it is governed by these conditions. So once it causes this, suddenly it experiences a certain drop in the velocity, okay. I'm not going into a bit of mathematical equations and all to analyze this because it turns out to be complicated in this case of converging diverging nozzles, which is not required for gate as of now, okay. So if this is P star and this is PB here, then there is a sudden jump is what you will observe at these conditions, okay, at this set of conditions actually here, okay. So at this set of conditions, you will observe there is a sudden jump in the properties, and this sudden jump is normally called shock, okay. This sudden jump in the properties at this point, you can see. So sudden jump in properties is shock, okay. There is a sudden variation of pressure, temperature, all these things. There will be a sudden jump upstream jump actually. And here if you see, if you have this diverging part, okay, and shocks happen only in case of supersonics because it happens to the downstream of the throat actually here, okay. Let's see. If you have a shock here, shock is not like very thin, within some region, okay. So let us say this is actually a shock somewhere here. Then what happens here is, if the pressure is P1, T1 over 1, and here the situation is P2, T2 over 2, there is a sudden jump from this properties to this properties actually, okay. So now let us see how to analyze these properties, means how to calculate the downstream properties. That's the important idea actually, okay. So see here, if you do fluid flow analysis to that part of the section, means if I take this shock, so this is normal shock actually. Normal means basically perpendicular to the flow direction. You also have oblique shocks and all, which I'm not dealing as of now. Okay, so we have normal shocks. Even questions didn't come up to this level in GATE examination in the last 3 years, but anyway, for safety point of view, I'm just telling this. Okay, so if you see in this case of shocks, if you take this small control volume, okay, this is a normal shock, and here the velocity is u1 maybe, and pressure is p1, t1, density is o1, Mach number is m1 for example, and here on this side the conditions are velocity is u2, p2, rho2, t2, and this Mach number is m2 definitely, because if see, because of the shock, if velocity is changing and temperature is changing, then definitely Mach number also changes. Okay, now to solve this, to get these conditions, okay, P, O, T are the conditions actually, because if you can identify P, O and T, and also U2 you can measure by means of a pitot tube or something, then you can calculate what is the Mach number downstream of the shock actually. Okay, now let's see, in this case if you apply mass balance actually here, mass balance, then definitely you can understand rho1 u1 is equal to rho2 u2 at this point, correct? Because this area of cross section means within this small regime, the area of cross section will be very, very small, because normally it's a thin shock. Okay, so at this point, if you take the area of cross section of the shock as very fixed between the inlet and outlet, because within the small narrow region the area of cross section don't change much, so this is from the continuity equation. Okay, so you can say continuity equation gives you this. Continuity gives you this actually here. Okay, and if you apply momentum balance actually here, okay, so if you apply this momentum balance, you will get something like, see, if you apply momentum balance, normally here if the pressure is P1 and here if the pressure is P2, then P1 minus P2 times area is equal to, so this rate of change of momentum, which is rho u2 square minus rho2 u2 square minus rho1 u1 square times area actually here. Okay, so normally we have seen this in Reynolds transport theorem, that pressure sigma f is equal to summation of moment leaving out minus summation of momentum leaving in, coming in actually here. Okay, so that's how this equation is actually framed. You can see this area and this area gets cancelled actually here. Okay, and also energy, if you see energy balance, so since stagnation temperature will be same, stagnation temperature, this H0 at 1 is same as H0 at 2, or stagnation enthalpy before the shock means upstream of the shock is same as stagnation enthalpy downstream of the shock actually. Okay, now these are the 3 equations that we have. Okay, so these are the 3 equations, but you have 4 unknowns here, 1, 2, 3 and 4. Velocity is also there. Okay, means if these are the 4, then how these 4 are coming, P2, O2, T2 and U2 is what you have. So you have 4 unknowns, so we need one more equation. And what is that equation? Come on, see, you have 4 unknowns here. Let's say if I know these 4, then of course Mach number can be calculated depending on u1 and t1, because if I apply u1 by square root of gamma t1, I'll get Mach number, no issue. Okay, here I have to calculate these 4 quantities. Now I have these 3 equations, so I need one more equation. So what is that equation? Come on, what is that equation in that case? What is the 4th equation? What is the 4th equation that you have? These are the 3 which you know generally: mass conservation, momentum conservation and energy conservation. Here in this case, here I already told you there is an ideal gas which is flowing in this case. Okay, no Mach number relations, because you don't have any Mach number relation. You cannot actually, you have to generate that. Okay, you have to find out what is the relation between these Mach numbers. That's how you can identify. If this is known, then you can calculate this, correct? You actually have to derive some relation between these 2 Mach numbers. That's how you will come to know if this is the Mach number here, then what is the Mach number here, correct? You need one more equation. What is that? Any idea? because there are 4 unknowns. Okay, you have only 3 equations. You have to build one more equation. Yes, ideal gas equation. Fantastic. So we need equation of state. Equation of state actually. So equation of state, and if you take the substance as ideal gas, then this is P is equal to ORT. That's it. Okay. So P is equal to ORT. If it is some liquid or something, we might have got some other equation as equation of state. Okay. So depending on the real gas, if it is a real gas, we might have written Van der Waals equation. So depending on the things, we can actually write this equation of state. Okay. So this is for ideal gas because we have taken the gas which is flowing here is ideal gas. Okay. Clear? Now, if you simplify this and if you try to solve a bit of relation, so here the conditions are stars. So it is thought and Mach number is equal to 1 at this point, let's say. Okay, so thought and you have the Mach number is equal to 1. Then if you see the velocity, acoustic velocity at this point, if you call this A star, okay, because at this thought you have taken the Mach number, okay, because at any point you can calculate in some acoustic velocity of the disturbance, but this acoustic velocity changes along the length of the nozzle because temperature keeps changing along the length. So if temperature changes along the length, square root of gamma RT changes. So if square root of gamma RT changes, Mach number keeps changing and it touches 1 at this particular point. Okay, so at Mach number is equal to 1, what is the sonic velocity? That's what. Okay, means at this point what is the temperature? So let's say here the temperatures are P star, T star, okay, and rho star. Maybe if these are the conditions, then clearly this A star is given by square root of gamma R times T star. Okay, so this is the acoustic velocity in this case. And if you do a bit of analysis using these 4 unknowns and 4 equations, if you try to solve them and all by eliminating these pressures and all with the help of this state equations, okay, equation of states, if you try to understand, you will end up with some results which are like, on solving the 4 equations, what you will get is actually your A star square will be product of U1 and U2. This is one very much important equation which you will generate in this this analysis. Okay, so A star square is equal to U1 U2, and this equation in case of normal shocks is called Prandtl's equation. So this equation is called Prandtl equation, and this is very much important. This helps you a lot in calculating the things because you can calculate what is T star if the substance is given. Okay, if the substance is given, you can actually calculate what is T star actually, right? Because see guys, it's very easy for you how to do this. I'll just explain you with the help of an example. Let's say there is a nozzle. Okay, so this is a converging and diverging nozzle. If this is converging diverging nozzle, let's say I told you fluid is coming in with some velocity U1 and temperature T1, for example. Okay, if I told you there is some fluid which is coming at U1 and temperature T1, and you want to calculate what is this T star. What is this T star? Because if you calculate T star, you can calculate what is this A star square actually, because of this simple expression. Okay, because of this expression you can calculate this. Now if this is U1 and T1, how do you calculate this? We know for the substance, let's say for example if this is air, okay, so atmospheric air, so gamma is equal to 1.4 for example. Okay, then you have your T star by T naught is equal to how much it is? 1 by 1.2. We have calculated now 1 by 1.2, 0.833. Yeah, this is 0.833. Now depending on these conditions, you can actually calculate what is T naught. T naught is nothing but T1 into 1 plus gamma minus 1 by 2 Mach square. At this point you can also calculate Mach number, Mach 1 square actually. So let's say this is 1 at the upstream condition. Mach 1 square is nothing but, or Mach 1 is equal to U1 divided by square root of gamma R T1 actually. Okay, so T1 is known, U1 is known, you can calculate this. If you can calculate this, you can put it here, you can calculate what is T naught, and T naught remains same all over the zone actually. Okay, so that's how, if T naught remains same, then if you know T naught, if you multiply T naught, you can get what is T star. So you can get sonic velocity. We done it yesterday. Yeah, we have done this calculation yesterday. So we can actually calculate what is this sonic star. Okay, so A star means acoustic velocity at the max, at the third condition. Okay, is this clear to all of you? So please type in the chat box, is this clear to all of you? Of course I'm not deriving this, but you can actually get this equation by solving these 4 equations. Okay, and also you can get one more important relation between the Mach numbers, as one of you is telling. You will get Mach number 2 means Mach number at downstream at second condition, means the Mach number in this region, in the downstream region, Mach number 2 is equal to 1 plus gamma minus 1 by 2 Mach 1 square divided by, okay, so gamma times Mach 1 square minus gamma minus 1 by 2 actually here. Okay, so this is the relation which you will get for calculating the Mach numbers M2. Okay, so let's say if I give you M1, for example, if I give you this, you can calculate what is M1. So you can calculate MA2 depending on these conditions. Okay, and normally for air they have tables for different Mach numbers. Okay, in this expression, let's say for example, if I take air, for air Mach number 1 or Mach number downstream is equal to, if you put gamma equal to 1.4, this is 1 plus 0.2 Mach 1 square divided by, if you put 1.4 here, so 1.4 Mach 1 square minus 0.2. So this is how we get. So in this, the only thing that you should know is Mach number 1. So you have tables for that. Okay, without even doing calculations, let's say for example, if I give you U1 T1 and if I give you Mach number 1, if you put Mach number is equal to Mach number 1 value in this case, you will easily end up with calculating Mach number 2. Understood? So did you understand how to calculate downstream conditions of a shock? This is how. Of course, this is only for air. This is the main equation for any substance depending on your gamma. Okay, and this equation analysis is purely from these equations, just solving of these 4 equations. Okay, yes or no? So please type in the chat box. Is this clear? And normally in exams and all, if you see, they generally provide you this relation because people generally don't cannot remember this very effectively. But since I'm doing it many for many days and many years, I'm able to write this directly. Okay. So is this clear? Fine. And from this relation, you can get U2 easily, okay, because U1 is known. You can calculate T star, so A star is known. So A star square is equal to U1 into U2 is what you can calculate. Okay, so once you get U2, you can calculate what is P2, T2, all these things. Fine. And normally, actually, based on these 2 equations, we plot 2 different lines. If you plot this mass and energy, we'll plot the Fano line actually, and mass and momentum gives the Rayleigh's line. Okay, so normally if you see, there are 2 lines in this where we plot HS curves for shocks. HS curves, if you plot for mass and energy means the locations where the energy is same. If you try to plot them with same mass and same enthalpy on the HS curve, you will get a curve which is given by this name, Fano line, and this mass and momentum, if you see, this will get a Rayleigh's line. Rayleigh's line actually here. Okay, and plotting this graphs is not also very simple because we have to look into these 2 types of flows, what is Rayleigh flow and Fanny flows, but all this is in advanced gas dynamics, so I'm not touching it up down. Okay, main things where questions can come is basically from parts what we have done yesterday and also today up to this converging nozzles if they ask. Okay, maximum up to converging nozzles they can ask. Normally CD also not very comfortable to do mathematical analysis in GATE exam. Okay, and normal shocks, normally if they give, they can give you the relations actually. Now if this Mach number 2 is known, Mach number 2 is equal to U2 by square root of gamma R T2 is what you can calculate, and U2 can be written as A star square by U1 by square root of gamma R T2. That's it. Okay, so from this equation you can calculate what is T2 again, because Mach number 2 is known, so this is known, U1 is known, so anyway this is also known, gamma is known, R is known, so you can get what is T2. So that using all this set of equations and all, if you know T2, then again you can go for pressure equations. Okay, so depending on all the things we can get this. Okay, so is this clear to all? So shall we solve some questions based on these flows, these shocks and all, normal shocks whatever. Today's the class is slightly concept heavy, correct? I have started from area versus flow, area versus velocity variations. Then after converging nozzle, we have done certain differentiations, okay? And then this shocks, okay? So anyway, let's see. Let us solve some bit of questions. So I'll put this slide in the last, better revision slide. Before this 2-minute summary, we'll put, okay? So let's see. Let us solve this question. An aircraft flies at Mach number is equal to 2.3 at an about 11 km standard altitude. The temperature at the stagnation point is dash Kelvin. Okay, so let's see. This is sea level, for example. So this is sea level. Then there is an aeroplane which is flying at this point. Okay, so there is an aeroplane which is flying at this point. So let's say this is the stagnation point, and this plane is flying at an altitude of 11 kilometers actually. Okay, so this plane is flying at an altitude of 11 kilometers actually. Okay, so 11 kilometers is what we are telling, and this is flowing at a Mach number 2.3. So this plane is moving at a Mach number which is 2.3. So what is the stagnation temperature? That's what we need from this question. Okay, so let's see how we can do this. So normally in this atmosphere, we have the temperature variation, which I have given you in fluid mechanics. You remember? Pressure variation in atmosphere. I told you exponentially it varies. Okay, exponential, it varies with power law kind of model. I was telling you in fluid statics I was talking about. Okay, so T at any elevation is given by T0 minus alpha z, where T0 is equal to 288.16 Kelvin roughly. Okay. Normally 15 degrees Celsius, normal temperature conditions, So T is equal to T0 minus alpha z is what you have. Now alpha is 6.5 Kelvin per kilometer. You know this, we have talked about this already. Okay, so this is 6.5 Kelvin per kilometer. These two values I have given you when I'm teaching this fluid mechanics, in fluid statics. You remember we have seen in atmosphere P variation is power law kind model. You know, we have solved the hydrostatic equation. You remember this? We have done all these things. Yes or no? You remember dP by dz is equal to minus OZ. Then density we have taken from P equal to ORT. Then T we have substituted this. All these things we have done there. If you remember, it's good. If you forget, you please once go to the fluid statics lecture. Okay. So anyway, let's see here. So this gives you temperature at altitude of 11 kilometers is equal to 288.16 minus alpha 6.5 Kelvin per kilometer. So let us put this also in kilometer, 11 kilometers, because this is per kilometer. So this is also in kilometer. So total will be in Kelvin. So this will be in Kelvin. So temperature at elevation of Z is equal to 11 kilometers is something like 288.16 minus 288.16 minus 6.5 into 11. 6.5 into 11, 216.66 Kelvin. 216.66 Kelvin actually. Now what is the stagnation temperature? We have seen the relation. Ts is equal to, stagnation temperature is T into 1 plus gamma minus 1 by 2 Mach square is what you get. Okay, so this tells you temperature is 216.66 into 1 plus gamma minus 1 by 2. This is atmosphere, standard atmosphere. So gamma is 1.4. So 0.2 into 2.3 square. Okay, so this is 2.3 square. So this gives you the stagnation temperature in some Kelvin actually. Okay, so stagnation temperature is some Kelvin. Got it? Yeah, this is 216.66. So what is the stagnation temperature in Kelvin? 5.92 is coming for what? No, stagnation temperature will be definitely more than this, no? So let's see, because we had this relation. So Mach number is 2.3, which is given. So 2.3 whole square, 2.3 whole square into 0.2 into 0.2, this value plus 1. So 2.058 into 216.66. So 445.88 Kelvin. 445.88 Kelvin is the actual temperature at this stagnation conditions. Okay, so 445.88 is the value that you got. Okay, within you are getting 544. How come? Because this is the expression, right? That's what. See, don't substitute this directly 288 here as temperature. This is the at Z is equal to 0 at this sea level, normal temperature conditions, 15 degrees Celsius roughly. Okay, so from there we can calculate what would be the temperature at elevation of 11 kilometers. Okay, so anyway, this is one question where we got 445.88 Kelvin. Okay, so this is 445.88 Kelvin. So let's go to the next question quickly. So let us solve this question. A large vacuum tank held at 60 kilopascals absolute sucks sea level standard air to a converging nozzle whose throat diameter is 3 centimeters. The Mach number at the throat is dash. Okay, a large vacuum tank at 60 kilopascals. Okay, so fine. See here, there is a converging nozzle. First of all, there is a converging nozzle like this. Now this converging nozzle is discharging into a tank. This converging nozzle is discharging into a tank actually here. Okay, so this is discharging into a tank and it is taking from atmosphere. This is taking from atmosphere. Clear? So there is a tank which is to which this nozzle is getting discharged. Okay, so here the conditions are P0, T0, O0, and here it is P of the tank. So what is P of the tank actually here? P absolute, which is 60 kilopascals, of course. Okay, so this quantity is pressure of the tank, so which is nothing but P star, because this is the pressure equal to this. So P star is actually how much? 60 kilopascals. So let's see. Given P star is equal to, okay, so P star is equal to, what is P star? 60 kilopascals. Okay, because if the tank is at 60 kilopascals, then that definitely this throat will also be at 60 kilopascals, because if you want to have the maximum mass flow rate, is at 60 kilopascals, sucks sea level standard air to a converging nozzle whose throat diameter is 3 centimeters, which means A star is equal to pi by 4 d square d star square. So A star, the flow at this point is, I mean this area of cross section is 3 centimeters, so 0.03 whole square. So A star at this point is some meters actually here. Okay, so this is the meters that you have here, meters. Okay, so A star is equal to some amount of meters. So let's see, pi by 4 into 0.03 whole square, 0.03 whole square into pi by 4. Okay, so into pi by 4, 0.0007, so 7.06 into 10 power minus 4, 7.06 into 10 to the power minus 4 into 10 to the power minus 4 meter square. So this is A star. Now if you want to calculate what is the Mach number, you should know what is velocity at that condition and also your T star. Okay, so let's see this P star and P0. Okay, so what is P0? P0 is not given to you, so let's calculate mass flow rate is OAV, of course. So we need to calculate velocity first of all if you want to calculate Mach number. So Mach velocity is actually how much? That's the condition. Velocity at the exit square. So what is this value? This is 60 kilopascals. Okay, so tank condition is 60 kilopascals. This is sucking sea level standard air. Okay, so sea level standard air. So sea level, this P0 normally phase at static condition 101.325 kilopascals. This is P0 actually here at this case. Okay, so if this is P0, then we know P star by P0 for air, P star by P0 is equal to how much? P star by P0 is equal to P star by P0 is how much here? P star by P0 value for air is, we have calculated now today somewhere. Let's see, P star by P0 value we have calculated somewhere here, which is 0.528 something we have calculated. This atmospheric air, yes, we have calculated here 0.528. Okay, so this is 0.528. So this is 0.528. 0.528. Okay, so P star is actually 0.528 now. That's what we get. 0.528. Yes, V is coming 7.065 aspirant. Okay, fine. So this is P star actually, and this is the flow area. If you want Mach number, we can also relate this conditions using Mach number, right? So P star is known. I mean P star is not yet known to you. Okay, P star is known, which is 60 kilopascals. Fine. Then you can calculate what is stagnation enthalpy. So 60 by 101.325 I guess. Okay, so 60 by 101.325, this gives you again 0.59 or 0.528 I guess. We have to calculate the Mach number. Okay, so let's calculate the exit velocity. So how to calculate this exit velocity? First, T star by T naught, if you see, so T star by T naught actually. So this T star is also not known to you. We need Mach number at exit. Okay, so Mach number at exit is V by A star, definitely, because that's the sonic condition at that case. So A star can be calculated because A star is nothing but square root of gamma r into T star. So how to calculate this T star? That's the main important thing. Okay, so how to calculate this T star? Come on, how to calculate this T star? This relation again. So T star by T naught is there for atmospheric air. So T star can be calculated from this conditions because such sea level standard air. So T naught is 273 if you take at sea level, because standard temperature and pressure conditions, then we get this T star value. So if T star is calculated, then we can calculate what is A star, and if A star is calculated, then we should calculate what is this V from this T naught conditions. Okay, so this T naught, if we can calculate from T naught is equal to T times of 1 plus gamma minus 2 Mach square is what we have here, correct? So this is T star actually. So this is T star. So you can calculate, because T naught is known to you and T star is also known, so you can calculate Mach number directly, because this relation can actually help you at Mach is equal to 1, but here Mach is not equal to 1. So anyway, if you calculate this temperature at this point, that resolves all the issues, correct? So normally let's see what we have. T stagnation, T into 1 plus Mach square into gamma minus 1 by 2 actually here. So this gives you T naught is equal to T times of 1 plus, what is Mach number? A square by V square into gamma minus 1 by 2 actually. So we have to calculate what is this V square. Okay, we have to bring certain expression for velocity. So let's see, this velocity is equal to T naught minus T is equal to A square by V square times gamma minus 1 by 2 actually into temperature T. So if you divide this T here, we get T naught by T minus 1 is equal to A square by V square into gamma minus 1 by 2, of course. So V square is equal to A times 2 by gamma minus 1 into T naught by T minus 1. Okay, and deleting this will give a temperature here. Okay, I mean we'll give a square root here. If you delete this square, then you will have a temperature. But T naught is taken from atmospheric conditions because sea level standard air. So we can take this as 2.93. So if you simplify this, then you'll definitely get this Mach number, because this velocity can be calculated using T naught and T. So V can be calculated actually, and T naught is nothing but your atmospheric temperatures, and this T star, if you write, because T star by T naught can be calculated from this relation for air, 1 by 1.2. So what is that? 1 by 1.2, 0.833. So no need of this point. So T star by T naught is actually 0.833 is what you use. Then if you get T naught, you can calculate T star. So T star is actually, if you use T star, you'll get A star, and also here in this equation you'll get V actually here. Okay, so that gives you V by A. You're getting 0.792 maybe because Mach is V by A. So V we have calculated something like square root of J into 2 by gamma minus 1 into T naught by T star minus 1. We have converted everything in terms of this temperature clearly. So what we can do actually, this sonic velocity, square root of gamma r T star actually here. Okay, so you can calculate these values, and this is coming out to be 0.792. Okay, so this value is coming out to be 0.792 maybe. See, the basic thing is to just play with these relations. Okay, so these relations and also these relations actually. Okay, so if you just adjust them and if you try to solve, you will get the answer. So we were given stagnation pressure. Achha, stagnation pressure is given, then you can calculate Mach number, no, directly. Yeah, you can calculate the Mach number also, but to calculate this Mach number we need these things. Yes, so because of this calculation you can get this Mach number. Okay, basically to calculate the Mach number at somewhere in the flow, you can use this P naught actually. Okay, so P naught by P star is equal to 1 plus gamma minus 1 by 2 Mach square. All these things you can use. See, you know this relation. P naught by P exit, if you see, P naught by P exit is equal to 1 plus gamma minus 1 by 2 into Mach square whole power gamma upon gamma minus 1. Okay, so this is what we have. Only this is known, but this is not known to you. Okay, so that's why we are doing these calculations. Clear? So let's solve one more question before we leave. Come on, solve this question. Consider the isentropic flow in a channel of varying area from section 1 to section 2. Mach number at section 1 is 2. The desired velocity ratio is V2 by V1 is 1.2. Consider the correct statements. Come on, do this. I'll connect a poll, multiple choice, and I'll give you 150 seconds. Solve this. Yeah, you can use any of these two equations. Okay, so basically it's the play with pressure and temperature. That's it. Okay, come on, solve this question. Consider the isentropic flow in a channel of varying area, section 1 to section 2. Mach number at section 1 is 2. The desired velocity ratio is V2 by V1 is 1.2. Choose the correct statements. Channel is converging and channel is diverging. Mach number at section 2 is in the range of things like this. Come on, there's a Mach number at section 1 which is 2 and velocity has to increase. So identify the type of passes and also this Mach number at section 2. A and B converging and 2.7 to 3.1. Is it? I don't think it's converging, right? Because velocity is increasing in supersonic. So in supersonic, if velocity has to increase, then definitely it's a diverging nozzle, no? But this is converging. BC, yeah, I think it could be BC. So let's see. So this is definitely wrong. The reason for this is C. So let the poll end. Will work out. So see here. Solution. There is a passage actually here. So this is A1 and this is A2, section 2. Okay. So we have section 1 and section 2. So the Mach number at this point is 2. Okay, so this is 2.0, and clearly if this is velocity V1 and if this velocity is V2, V2 by V1 is actually 1.2. So this implies velocity increases. Okay, so V2 is actually greater than V1. So V2 is greater than V1 actually here. If V2 is greater than V1, that means fluid is actually accelerating in this case. Okay, so fluid is actually accelerating. So fluid is accelerating, and here at the inlet, this is a supersonic flow. Okay. Yeah, didn't see the options, fine. Okay, so therefore, fluid is accelerating at supersonic. Fluid is accelerating at supersonic conditions. Fluid is accelerating at supersonic conditions. Then, let's see if fluid is accelerating at supersonic conditions, then this implies, okay, so if fluid is accelerating at supersonic conditions, this implies passage is diverging. Passage is diverging. So this passage is diverging means one thing is very clear, your A2 is definitely more than A1 actually. Okay, so passage is diverging. So A2 is more than A1. So this is not converging, it is actually diverging. So C is one of the correct answers. Okay, then what could be the Mach number at the exit? Okay, so let's see. Mach number at the exit V2 is what you want. Okay, M2. So what is this values? Okay, so let's see. We have M2 is equal to V2 by acoustic velocity at 2 actually here. Okay, and this V2 is 1.2 times of V1 divided by A2 acoustic velocity. So if you want to calculate acoustic velocity, A2 is nothing but square root of gamma r T2. Okay, and T2 can be again written as, means if you do square on both sides. Okay, so M2 square is equal to 1.2 times of V1 square by A2 square. So which means gamma r times T2. T2 can be written as T0 at 2 divided by 1 plus gamma minus 1 by 2 times of Mach 2 square actually here. Okay, so that's what I can write. T0 2 divided by 1 plus gamma minus 1 by 2 times Mach 2 square actually here. And what about V1 square actually? So V1 square can be written as V1 is equal to Mach 1 into acoustic velocity here. And if you do square of this, because anyhow we need squares, so V1 square is equal to Mach 1 square times this A1 square. So A1 square is gamma r T1. So T1 is nothing but T01 divided by 1 plus gamma minus 1 by 2 MA1 square actually here. Okay, so this is the expressions. Now if you substitute this V1 square here, let's see what you'll get. So this gives you M2 square is equal to 1.2 square. 1.2 square is there here. So 1.2 square Mach 1 square gamma r T01 divided by 1 plus gamma minus 1 by 2 Mach 1 square, this term divided with this term gamma r T02 stagnation temperature plus 1 plus gamma 1 by 2 Mach 2 square actually here. So this is the equation. Yes or no? This is clear because these temperatures we are writing in terms of stagnations. Okay, and clearly this gamma r is constant and stagnation temperature do not change because this is an isentropic flow. So definitely this stagnation temperature remain same. So this gives you Mach 2 square is equal to 1.2 square times of 1 plus gamma is 1.4 because it is air. So if gamma is 1.4, this term is 0.2. So 1 plus 0.2 Mach 2 square divided by 1 plus 0.2 Mach 1 square. That's it. Okay, so this is the equation. Now clearly you have this Mach number 1 is equal to 2. So this is 4. Then definitely you can solve only one equation with one unknown. You can solve this Mach number 2. Okay, so if you solve, what is the values? Let's see. Mach 2 square is equal to, or if you simplify these equations, then this is 0.4 into 0.2 into 4, 0.8. So this is 1.8. So Mach square is equal to 1.2 square by 1.8. Let us see. 1.2 square by 1.8 actually here. Okay, so 0.8. So this is 0.8 plus 0.8 into 0.2. 0.8 into 0.2, 0.16 Mach 2 square actually here. Okay, so 1.1 minus 0.16, 0.84 Mach 2 square is equal to 0.8 actually. Okay, so is that what you're getting? Just simplify these equations. So you can see 1.2 square divided with, Mach 1 is actually how much? So what is the Mach number initially? So initial Mach number is 2. Fine. So if initial Mach number is 2, this is 0.4. This is 0.2 into 4 is 0.8 plus 1.8. So 1.2 whole square by 1.8. 1.2 whole square by 1.8. So this is 0.8 actually here. So 0.8 is on the right hand side plus 0.2 into 0.8 is actually 0.84 actually here. So 0.8 divided by 0.84, 0.84. So square root of this, I think we have reciprocated this now. Something is missing here. So just check. M2 can be written as V2 by A2 and V2 is actually written by 1.2 times V1, correct? So V2 is equal to 1.2 times V1, 1.2 times V1. So if you square this, M2 square is equal to 1.2 square V1 square by this A2 can be written as A2 square actually. So A2 square can be written as gamma r T2. So T2 can be written as T02 divided by this value 1 plus gamma minus 1 by 2 ma2 square, correct? This is correct. Yes. And what about v1 square? So v1 square is mach1 square into acoustic square. So mach1 square into gamma r T01 divided by this 1 plus gamma minus 1 by 2 ma1 square actually here. So if you use these equations, I think this term we have missed. Okay, v1 square is actually having this m1 square. So we have m1 square. So there comes a 4 here in the multiplication. Okay, because this v1 square, when you are writing this quantity, this ma1 square is also there. So if you write this ma1 square, we'll get 1 4 here. So that brings something like 4 on this side. It brings 4 on this side here. Okay, so it brings 4. So then this equation changes slightly, with coefficients will change. So these calculations are slight hectic, but you have to do carefully. ma2 square. So again, if you see ma2 square is equal to 1.2 square by this 0.8 into 4, 3.2. So this is 3.2 times 1 plus 0.2 ma2 square actually here. Okay, so if you simplify this, you'll get the answer. Just see, ma2 square is equal to 3.2 plus 3.2 into 0.2, roughly 0.64. 3.2 into 0.2, 0.64 ma2 square. So this equation gives you Mach number is equal to 1 minus 0.64 is 0.36, 3.2 divided by 0.36, 3.2 divided by 0.36. Okay, so square root of this 2.981. 2.981 is the Mach number at the second location. Okay, so these calculations has to be done little carefully. If you forget any of the terms, if you miss one gamma or something, then results will change. So anyway, 2.981 is somewhere here. 2.9 is within this regime, but it is not here. So B is the correct answer and D is the wrong answer. Okay, so B and C are the correct answers here in this case. So yeah, I think some of you have answered. Nitin, good. Both of you have answered. I mean, you have answered it correctly. 135.61 seconds. Good. Okay, so anyway, I think I have one more question, but anyway, you please try out this question. You can calculate this using the downstream properties. And yeah, so today we were talking about the compressible flows, basically area velocity relations, then after isentropic flow in nozzles, and we were talking about normal shock. So these are the things that we have discussed today. Okay, so that's all from the fast track course. Okay, fine. I hope all of you might have got some knowledge from this fast track course. And did you all find it helpful? Can we do it for your next batch? All of you. Yeah. Do you all find this course useful? Do you suggest this course, this fast track, for your next upcoming batch? Yeah. Okay. See, the only thing is, we guys are engineers. That's it. Okay. You have to do a bit of mathematical analysis to understand things. That's all. Yeah, you have to do a revision a bit. We have Maha revision sessions, and also this revision 2 questions is also coming up. Fine. Okay, so if you have any questions, you can ask me, or else we can wind up for now. We'll miss you. Yeah, even I miss you too. But anytime, if you want to contact, definitely you can join this Telegram group actually. So this is the Telegram group ID. So you can always come there and you can discuss a few things if you want. Okay. PYQ it's not there, but definitely have revision 2 questions. Okay. We'll all see you again for revision 2 some question solving. Because PYQs you have everywhere. Okay. No need of again solving PYQs for us. Okay, but it's very important for you to solve PYQs. Okay, and the solutions of PYQs are there in plenty of places. In everywhere we have taken, it's there. Okay, so again, there is no necessity of separately solving PYQs unnecessarily. So we do this. Yeah, thank you all. We'll meet soon. Okay, on YouTube again. Bye. Take care.